All right, so today we're going to talk about electron spin, okay? Because, right, for the hydrogen atom, this is not that important. There's one electron. Its spin isn't really too relevant to the properties of the atom and the molecule, right? But as we start talking about multi-electron systems, right, helium atom and beyond, okay, in those cases, the electron spin is going to matter. In those cases, we need to be concerned about what that spin is and some of the properties of the spin. So we'll kind of talk about that today. Okay. So the electron spin was originally discovered around the 1920s, right? When it was kind of discovered that an electron itself has its own kind of inherent angular momentum, and they discovered that by the fact that the electron can be deflected by a magnetic field. That essentially, right, this electron, right, is a charge. A moving charge can generate a magnetic field. So the electron itself having some type of angular momentum means that it's generating its own magnetic field, which then can interact with other magnetic fields and can affect its motion, okay, through that interaction between the magnetic fields. Right, and so it was originally, I mean, this is called like electron spin because the idea was the electron is, say, spinning about its axis, just like the Earth rotates around its axis, right? It's spinning, and that spin generates an angular momentum, which again is some moving type of charge, which generates a magnetic field. Okay, this isn't the most accurate description of the motion of an electron. And what electron spin is, because if you were to, right, I mean, think about this, the size of an electron is extremely tiny, right? So you think about how fast that thing has to spin to generate the type of magnetic field that it does, that's observed in experiments. You would get the case where this electron is spinning faster than the speed of light. Okay? It's not really possible, right? And so the electron spin is not really just an electron, say, spinning about its axis, but that's how we think about it. Okay, and that's fine to kind of think in that way. I just want to mention that, like, it really, just like an electron orbiting a nucleus, it's not really that you have an electron in a nice orbital around a nucleus, like you think of the sun or the Earth orbiting the sun, right? Right, this is in Galileo's time. We don't think of the sun revolving around the Earth, right? We know the Earth revolves around the sun, right? So the electron revolves around a nucleus, right, is how we think of it classically, right? But in quantum mechanics, it's not quite that the electron has this nice, clean path of how it's moving around a nucleus, right? It more has some probability of distribution, and it's existing in places around the nucleus and things like that, right? And it has some inherent angular momentum based off of its wave function and things of that nature, right? But again, it doesn't necessarily have a set spin, okay, or set like path that it's taking. Sorry. Okay. So what is the electron spin? Well, we can describe the electron spin by two quantum numbers, right? Electron spin is it. You can think of it as an angular momentum, right? An angular momentum, we'll talk about the total angular momentum and the angular momentum in a certain direction, right? And so our total angular momentum quantum number is S here, right? S gives us the total angular momentum, okay? So the total angular momentum for an electron spin is always 1/2, okay? Always a half, right? There's right, angular momentum of an electron around the nucleus can be different, right? It can depend on what the L quantum number is, which can range from 0 up to n, right? But or n minus 1, I should say, right? L goes from 0 to n minus 1, right? And so L can change, right? The total angular momentum of the orbit around a nucleus can change, but the total spin of an electron is an inherent property of that electron and is always 1/2. Right? Every particle has that, right? The protons and neutrons have inherent spins, right? Light has an inherent spin. It's 1, for example. Okay, so every fundamental particle has some sort of inherent angular momentum, some inherent spin associated to it, which are related to inherent properties of the subatomic particles that make up these electrons and protons and things like that, muons and quarks and so on. And so this is, getting where the spin comes from, why it's a half, other things like that are, well beyond what we're going to talk about here. Okay, but it deals with particle physics and things of that nature. Okay, but for us, we're just concerned about the fact that that electron spin is 1/2. Okay, and the fact that it is half and not a whole integer, so photon, right? Light is 1, electron is a half. This is going to have very specific implications to certain properties of these things, and we'll talk more about that in a minute, right? But so S is the total angular momentum, total spin quantum number, right? And so the total spin momentum, right? Just like for L, right? So right for the total angular momentum, right? L squared total angular momentum, right, is related with L plus 1 h bar squared. Okay, right? So it's the same thing for S, right? So replace L's with S's, and it's the exact same thing, right? Because again, spin of a particle is same type of thing as an angular momentum, right? Right, because something spinning is generating angular momentum, right? So again, so you have S is equal to little s times little s plus 1 times h bar squared, right? So then the magnitude of the angular momentum, right? Right, the square root of this, right, is just the square root of s times s plus 1, which in case for an electron is always a half, so it's just 1/2 times 1/2 plus 1 square root times h bar, which is just square root of 3 over 4 times h bar. Okay, so that is the total spin of an electron. Okay, and then like angular momentum, we can talk about the total angular momentum, we can talk about the angular momentum in the z direction. So in this case, we'll talk about the spin in the z direction, m sub s, right? Which, right, m sub l, right, has values of negative L to 0 to L, right? And as m sub s is the same thing. It goes from negative s to positive s, right, in integer steps. So negative s is minus 1/2. Increase it by an integer, which is 1, right? Increase it by 1, and you get to 1/2, which is s, right? So those are the only two possible values, right, for the spin of electrons. So it can either be plus 1/2 or minus 1/2, okay? And we refer to the plus 1/2 as being spin up, okay, and the minus 1/2 as being spin down. Okay? So often I'll use the term spin up electrons or spin down electrons, right? And that's referring to its angular momentum in the z direction as being plus 1/2 or minus 1/2. Okay, and often we'll also use the labels of alpha and beta. So alpha will indicate spin up electrons, and beta will indicate spin down electrons. These are very common nomenclatures, common terminology used to talk about the spin of an electron. Okay, so we'll talk about alpha electrons, beta electrons. That's just up spin, down spin electrons. Okay. Right, and so when we talk about molecules, okay, we'll have many electrons. Each electron will have its own spin. It will be plus 1/2 or minus 1/2 in terms of its spin in the z direction. Okay, and the total number of alpha electrons, right, spin up electrons versus spin down electrons, beta electrons, determines certain properties of the electronic state of that wave function of your molecule. Okay. So if you have the same number of spin up and spin down electrons, right, typically all your electrons are then paired, right? You have spin up electron, spin down electron, all these things are paired up with each other, okay? That is going to be a singlet state, is what it's called. Okay? And it's called a singlet state because it's singly degenerate. There's only one way I can pair up all my electrons, right? It's just pair them up, and that's it, right? And so, right, the total spin of that molecule that has this, that's a singlet state is going to just equal 0, right? Because you have equal up and equal down, okay? And again, this is when the number of alpha and beta electrons are the same, okay? When they differ by 1, right, that means you have one extra electron, right? Let's say it's an alpha electron, right, spin up. I have one extra spin up electron, right? That is going to be a doublet state, okay? And it's called a doublet state because it's doubly degenerate, right? Because that extra electron could be spin up or it could be spin down, and it doesn't matter. Spin up, spin down, same energy, same state, basically, right? I mean, technically they're different because the electron has different direction of its spin, but ignoring any type of magnetic fields, okay? So this is all assuming no external magnetic fields, right? Your doublet state has then just one energy level that's doubly degenerate, okay? And this is where NMR comes in and other things like that when we talk about spectroscopy and such, right? NMR, you put these things in magnetic field and you change the energy levels of the spin up and spin down states, and you split them and things like that, and that's how you get these different peaks and everything else that goes on in NMR. It has to do with the spins, right, and the degeneracy of your states and things like that for your nuclei, right? So NMR is measuring for nuclei. There's EPR that measures it for electrons, but right. And so again, in this table, it's talking about, so a triplet state has 2 extra electrons of one spin, say 2 spin up electrons, okay? Well, I can have 2 spin up electrons, I could have both those electrons spin down, and that's the same energy. And then there's a combination of where I can take like spin up and spin down to make a triplet state, and we won't go into that right now, but there's 3 different ways you can put in your electrons to have this overall total spin of 1, right, and have a triplet state and again, a triplet state is a triply degenerate, okay? And then you can keep on going and going with quartet, quintet states, right? So these labels that we talk about, spin states, singlet, triplet, doublet, so on and so forth, is referring to degeneracy of these states. It's very important when you talk about, you know, the molecules and things like that, and their spins, okay? And so, yeah. Okay. And so, as just a review, right, electrons. All right, so finally, we'll kind of, the whole point of talking about a lot of these electron spins, besides talking about these singlet, triplet, and other type states, is talking about this Pauli exclusion principle, which states, right, that no 2 electrons can have the exact same quantum number, which means they can't occupy the same region of space. Okay, because right, these quantum numbers describe what orbitals the electrons are in, what their angular momentum are, their spins, and so on and so forth, right? So if 2 electrons have the same values of quantum numbers, that means they're occupying the exact same space, right? So what this means for our molecules, right, is that then, right, for a given molecule, right, I have some orbital that has some energy, okay, right? That means I can only put 2 electrons in an orbital, right, because if I put more than 2 electrons in that orbital, right, then this electron and this electron are now going to have the exact same set of quantum numbers. They're occupying the same space, and that can't happen, right? So I always have to have at most 2 electrons in an orbital, and those 2 electrons have to have opposite spin. Okay? And this is related to the fact that these electrons have half integer spins, and they're what are called fermions. Okay, fermions, right, are particles that are anti-symmetric with exchange to 2 particles. So if I have psi R1, R2, this is going to equal minus psi R2, R1. Okay, so I've just exchanged the labels between electrons 1 and 2. The wave function has to be the negative of itself. It has to be anti-symmetric is what that's called. And basically, if those 2 electrons occupy the exact same space, then this wave function can't exist. Like, it has to be 0 everywhere if that were to be the case, right? So these electrons can't occupy the exact same space in order for this anti-symmetry to hold. Okay, and this is a property of half integer spin particles, right? Light is not a half integer spin; it's a whole integer spin. Spin of 1. It is a boson. Okay. And so it doesn't satisfy, it doesn't need to be anti-symmetric, it's actually symmetric. And so that means that you can have multiple photons in the exact same region of space, okay? And this is true for example, the helium nucleus, right, which is an integer spin, okay, it has a spin of 1, helium nucleus with its 2 protons and 2 neutrons, right? That helium nucleus is considered a boson, and what happens is when you cool down helium to a liquid form, okay, the atoms, right, the nuclei of those heliums can occupy the same region of space as each other, and it creates this boson liquid, this super fluid, and has really weird properties. So if you were to Google, liquid helium or something like that, you'd see some really interesting videos of this liquid helium. It's almost near 0 Kelvin, right? But it can like flow up over and around the walls of the container, and all sorts of weird stuff, right? And it's because it's a boson that has these weird properties and things like that. And so these spins of these fundamental particles play key roles in their properties. And in case for electrons, they're fermions, they're antisymmetric, okay? Right, this is antisymmetry here, right? So this antisymmetric, right? So this antisymmetry is why no 2 electrons can occupy the exact same orbitals, okay? All right, so finally we'll just kind of finish up these lecture slides with some clicker questions here to kind of go over them together. You can pause the video. I'm going to just go straight into the answers or whatever, but you can pause video, right, to think about it yourself if you like before I discuss the answer, right? So here the question is, which statement is true about the hydrogen atom, right? And so A here, the energy does not depend on the quantum number L. Okay, that's true, right? So already we know that one's true. So the rest of these has got to be false, right? Energies become more widely separated as the principal quantum number n increases. That's false because the energy depends on 1 over n squared, okay? And so the energy spacings are going to get smaller, okay? So it's smaller, right? Total quantum number of nodes in a wave function is equal to twice the control quantum number. That's not true. It's just equal to the principal quantum number n minus 1, right? N minus 1, okay? And then the 3D XY orbital has 1 angular node and 1 radial node, okay? That is not true. This has this has 2 angular nodes and no radial nodes, okay? Right. All right. Okay. Next clicker question here. The absence of a magnetic field, the order of the hydrogen atom energy levels is what? Okay. Well, we know the hydrogen atom energy, right? N is equal to, some numbers here. I'm just going to call it constant. I don't know, whatever they are, right? Times the atomic number, right? Z squared for n squared, right? So it just depends on the quantum number n, right? And it's a negative value, okay? That's the other key thing here. It's negative 1 over n squared, right? Which means as n increases, this number gets smaller. And so I start right at E1, E2, E3, and so on and so forth, right? Where, right, my energy E equals 0 is up here, right? And these are all negative, right? These are all less than 0. Okay, and so we know that. So that means that the most negative, right, number, right, the lowest number here is going to be the 1s orbital. So automatically no, it's not A and not D, right? And so then it's a question of, is it P or C? Well, here, right, you have the 2s and 2p, right? Well, the energy just depends on n, doesn't depend on the different values of L. So these things are equal to each other, right? And then this, right, is greater. So it's going to be B here, right? It's not C because these have to be equal, right? So it's B. All right. And then the final question for this set of lectures is, if a hydrogen atom with the 1s configuration is placed in the magnetic field, the electron spin degeneracy will be removed and the number of states with different energies will be what? Right. So, right, our hydrogen atom has one electron, right, and it's a spin up or spin down, okay, right, that one electron, right, one electron, okay, which means if it's spin up in a magnetic field, you're going to interact with it differently versus spin down, right, and so there's going to be a total of 2 states when you put the hydrogen atom in an external magnetic field, because again, you have what's considered a doublet state, right? The energy of the spin up, an electron being spin up versus spin down, is the same outside of the magnetic field, but inside the magnetic field, these are going to be different. It's going to split them, and you're going to have a doublet. Okay, right. So again, because there's n alpha minus n beta is equal to 1 here, right? It's not 0, right? This is a doublet. And so in a magnetic field, this doubly degenerate state will no longer be doubly degenerate, and I will have 2 independent states from each other, right? And this is how, again, something like EPR works, is by breaking the degeneracy of these states in the magnetic field. Okay, and that is the last clicker question, the last slide for this part of the lecture, right? And we'll see you next time.